This was prepared by the DC-6 section of the Flight Training Center, United Airlines. One of the most reliable reciprocating engines developed is the Pratt & Whitney R2800. This engine powers all DC-6s in the United Airlines fleet. The reliability of this engine can be demonstrated in that the mandatory time limit on engine change is 3,000 hours for dry-rated and 2,500 hours for wet-rated engines. A thorough understanding of the operation and knowledge of limitations will aid you in achieving the time limit on these engines. The R2800 engine is an 18-cylinder, twin-row, radial, air-cooled engine with a single-stage, two-speed integral supercharger. It uses 130 octane fuel. The takeoff rating of the engine is 2,050 bhp dry and 2,400 bhp with water injection. The engine is broken down into 6 sections for identification and location of component parts. These are 1. The front section, 2. The front accessory section, 3. The crankcase section, 4. The blower section, 5. The intermediate rear section, and 6. The rear section. Each engine has an independent oil system. Oil is gravity fed from the oil tank to the engine-driven oil pump. Then it is delivered under pressure to the engine. Oil is collected in the lower part of the engine by scavenge pumps and returned through the oil cooler back to the oil tank. The oil tank is mounted in the rear section forward of the firewall. Tank capacity is 37.5 gallons, 35 gallons of which is usable in normal operation. 2.5 gallons is reserved for feather pump operation. There is additional space in the tank for expansion and foaming. A hopper inside the tank permits warm oil to be routed back to the engine. This feature provides a more rapid warm-up of engine oil supply. Each oil tank is equipped with an emergency shut-off valve at the bottom of the tank. These valves are cable connected to the 4 firewall shut-off handles below the glare shield in the cockpit. The oil supply to the feather pump comes through another line and is not affected by the emergency shut-off valve. The feather pump itself acts as a shut-off valve when not in use. Oil is gravity-fed from the oil tank to the engine-driven pump mounted in the rear section. The pump delivers oil through the oil screen for distribution to the engine. A check valve in the oil screen prevents oil from gravity feeding into the engine when it is shut down. If the oil screen becomes clogged, oil will bypass the screen. There is an accessories drain can mounted in the lower right side of the nacelle. Drain oil from various units is collected in the can. There is a manual drain valve accessible from outside in the line coming from the bottom of the can. The can is normally drained by ground servicemen. If the drain oil should reach the level of the upper port, it will drain overboard because this is an open line. The oil returned from the engine is too hot for reuse, so it is routed from the scavenge pumps through the oil cooler before being returned to the tank. The oil cooler is mounted on the bottom of the nacelle. Cooling is controlled by an air exit door, which governs the amount of air passing over the oil cooler radiator, and by a selector valve operated by oil viscosity, which can completely bypass the cooler if cooling is not necessary, or route oil through the radiator for cooling. In the center, or off position, there is no power to the oil cooler door actuator motor, and the doors will remain in position. The switch operates as a toggle switch in either the open or closed position. When the switch is released, it will return to the off position. There is a brake on the actuating motor that prevents coasting when the switch is released. Also, there are limit switches at the full open and closed position to protect the actuating motor. When the switches are in the automatic position, a thermostat unit located in the oil line between the cooler and the tank inlet senses oil temperature and sends signals to the oil cooler door actuator motor to control oil temperature as necessary. Oil temperature is normally controlled to approximately 70 degrees by positioning of the oil cooler door. However, under some normal operating conditions, oil temperature will be higher, even though the door is fully open, or lower, even though the door is fully closed. There are 3 sets of gauges in the engine oil system. These are all dual gauges. The left gauge of each pair shows engines number 1 and number 2. The right gauge shows engines number 3 and number 4. These gauges are 1. The oil quantity on the left, located on the overhead panel. 2. Oil temperature. And 3. Oil pressure on the engine instrument panel. Oil quantity is measured by a float-actuated Magnuson transmitter mounted on the tank. 26 volts AC is taken from the engine instrument transformer through the respective engine instrument fuse. The quantity gauges are on the overhead instrument panel. The full mark indicates 35 gallons. It does not indicate the 2.5 gallon feather reserve. Engine oil pressure is taken downstream of the engine-driven pump by a Magnuson transmitter. It is powered by 26 volts AC from the engine instrument transformer through the respective engine instrument fuse. The gauges are mounted on the engine instrument panel and register pressure in pounds per square inch. The oil temperature probe is mounted just downstream of the emergency shutoff valve in the engine oil supply line. The probe is a resistance bulb powered by 28 volts DC through a circuit breaker on the main circuit breaker panel. The oil temperature measured is that of the oil delivered to the engine. The oil temperature gauges are mounted on the engine instrument panel. Engine oil is diluted, if conditions warrant, by an oil dilution solenoid valve. This valve is located in the main oil line and is controlled by one of 4 toggle switches mounted on the aft overhead panel. 28 volt DC power is drawn from the bus through a single circuit breaker to the 4 switches. The fuel boost switches must be on for oil dilution, since the fuel is tapped off upstream of the engine-driven fuel pump. The oil system in the R2800 engine has proven to be a very reliable system. Periodic checks of oil quantity, pressure, and temperature should give ample warning of any abnormal or emergency situation. The next system we will discuss is the engine fuel system. Each engine has an independent fuel system. From the firewall shutoff valve, fuel is supplied to the engine-driven fuel pump. This is a positive displacement pump and has a bypass to permit booster pump fuel pressure to reach the engine for starting or in case of engine-driven pump failure. It also has a pressure relief valve to return excess fuel to the inlet side. From the pump, fuel is supplied to the carburetor. The carburetor, mounted on the upper part of the intermediate rear section, is a pressure injection carburetor. It is composed of 4 units. 1, the throttle unit to control airflow. 2 and 3, the pressure regulator unit and the fuel control unit, are used to control fuel-air ratio. And number 4, the automatic mixture control unit to adjust fuel-air ratio for changes in altitude. Fuel and air are not mixed in the carburetor. Airflow is sensed and fuel is metered to provide proper fuel-air ratio and injected, under pressure from the fuel pump, into the blower impeller, where it is mixed with air. To provide ample fuel flow for smooth engine operation as throttles are advanced, an accelerator pump is provided, which momentarily supplies additional fuel flow through the pressure regulator unit. In the fuel pressure system, there is also a red warning light mounted between the fuel pressure gauges that will illuminate whenever fuel pressure falls below 18 psi. 4 fuel pressure isolation switches are mounted on the lower left engine instrument panel. The isolation switches are used to turn off the system of an engine that has been feathered, or to check the warning systems on pre-flight. There are 2 float-operated check valves in the carburetor that return any vapors accumulated to the inboard main tanks. Carburetor heat is supplied by a preheat door mounted in the intake. It is operated by mechanically linked carburetor heat levers mounted on the lower right face of the control pedestal. Operating the lever positions the door to allow varying amounts of air taken from inside the cowling, which has been heated by passing over the exhaust stacks and cylinders. There is a water trap mounted in the intake to remove moisture from the air. A drain vents this moisture overboard. The dual indicating carburetor air temperature gauges are mounted on the engine instrument panel. The carburetor air temperature probe is mounted in the air intake above the throttle plates. It is a resistance bulb powered by 28 volts DC. Payload, the amount of revenue-producing weight the DC-6 can carry, is of prime importance to our operations. Without changing any major components of the aircraft, raising this weight allowance is of great benefit to operating costs. In high-density seating aircraft, the DC-6BT Tourist and the DC-6A cargo aircraft, this is accomplished by use of an anti-detonation injection fluid, or ADI, a water-alcohol mixture, in the engines which permits the safe use of higher takeoff power settings. For any given throttle setting, varying the amount of fuel mixed with the intake air will give a wide range of power and temperature variations. The best power ratio while giving maximum power, also develops a high cylinder head temperature, leading to possible detonation at high power settings. The auto-rich position of the mixture control, used at all high power settings, provides additional fuel for cooling. This results in a power loss due to excess fuel. To provide maximum takeoff power without sacrificing the power loss due to the excess fuel for cooling, the fuel-air ratio is set at best power, and the water-alcohol mixture is injected into the fuel-air mixture to accomplish this cooling. Using this ADI fluid permits an increase of approximately 350 horsepower per engine, allowing higher takeoff gross weights. ADI fluid is a mixture of 50% methyl alcohol and 50% demineralized water. No power increase is derived from the alcohol. It merely serves to keep the water from freezing. Only DC-6BT tourists and DC-6A cargo aircraft use ADI. Although the system is installed in some other aircraft, it is deactivated and is not used. The ADI system consists of a supply tank, an ADI pump, a water regulator, and an injection nozzle. Is mounted below the supply tank. On the forward bulkhead, the water regulator is mounted for inboard engine rear section, and in the aft portion of the outboard nacelle in the fuel for the outboard engine, the impeller. The tank capacity is 10 gallons. The ADI system is activated by 4 off-on switches on the aft overhead panel in the cockpit. Turning a switch on furnishes DC power to the ADI pump through a pressure switch. This switch is activated by engine oil pressure, preventing ADI flow to a static engine. The ADI pump supplies fluid under pressure to the ADI regulator. The ADI switches, located on the aft overhead panel in the cockpit, and the ADI pressure lights to the right and below the engine instrument panel. The green pressure lights indicate only that water pressure is available. They do not necessarily indicate that water is flowing to the engine. The ADI regulator has 2 functions. It meters water to the blower impeller where it is mixed with the fuel, and it also closes a derichment valve which reduces fuel flow when the water pressure is available. The derichment valve is a safety device which ensures that either water or excess fuel is available at high power settings to prevent a serious engine overheat if water pressure fails. The proper operation of the derichment valve can be observed in the cockpit when water is turned on at high power settings. Fuel flow should decrease. Quantity gauges for each ADI tank are on the overhead instrument panel. They are float-type DC gauges. To provide the necessary manifold pressure for takeoff power and to offset the effects of the thinner air as altitude increases, the engine is provided with a built-in supercharger, commonly called the engine blower. There is a single compressor or blower housed in the blower section, geared to the rear end of the crankshaft by a gear train mounted in the intermediate rear section. The blower can be operated in either of 2 engine crankshaft blower impeller ratios. Low ratio is used for takeoff and all operations up to an altitude where desired power can no longer be maintained. High ratio is used above this altitude for additional manifold pressure. Engine oil pressure is required to engage either the high or low clutch. When insufficient oil pressure is available, the blower is disengaged. Oil pressure is directed to either the high or low clutch by an electrical selector valve controlled from the cockpit. This valve is spring-loaded to the low blower position. The engine supercharger or blower switches are located just above the windshield to the right of the cowl flap rheostats. Number 2 and number 3 are shown in the high blower position. Number 1 and 4 in the low blower position. After fuel and air are mixed in the blower section and delivered to the cylinders, it must be ignited. This is accomplished by the ignition system. The ignition system, mounted on each engine, is a low-tension system. That is, the voltage generated is kept at a low potential until close to the spark plugs. There are several advantages to this system, the main one being prevention of flashovers or arcing in the distributors or wiring harness, and less radio interference. The electrical energy is produced by the engine-driven magneto in the form of low-voltage pulses. These pulses are passed to the distributors where breaker points chop the pulses into sharp surges and distribute each surge to the correct ignition coil by means of carbon brushes rotating across segment plates in the distributor base. Each segment plate being connected to an ignition coil in correct sequence. The low voltage surge, when it reaches the ignition coil, is transformed into a high voltage surge and fed through the short high tension lead to the adjacent spark plug, across its spark gap to ground, firing the spark plug. Each ignition system is completely dual. There are 2 sets of poles to each rotor magnet in the magneto, each of which generates current in one of a pair of magneto windings. There are 2 distributors, 2 transformers in each ignition coil, and 2 spark plugs in each cylinder. Thus, if there is a malfunction in one ignition system, the other will continue to function, although engine efficiency will be reduced. The magneto is mounted on the front accessory section in the 12 o'clock position. The 2 distributors are mounted on either side of the magneto. The wiring harness circles the engine at the base of the cylinders. The coils are mounted on top of the respective cylinders. To control ignition, there are 4 mag switches mounted on the overhead panel. Each is a 4-position switch. In the off position, both magnetos are grounded and no ignition can occur. In the left position, the right magneto is grounded, so you are checking the operation of the left magneto system. The right position checks the right system. On both grounds are removed and both ignition systems operate. Because a lean fuel-air mixture burns slower, the ignition system is provided with a mechanism to advance the spark timing to allow a longer burning time when the engine is cruise leaned. The advance is accomplished by a solenoid valve which provides engine oil pressure to change the magneto and distributor drives forward in the timing cycle. This permits ignition to occur sooner on the power stroke. The spark advance switches are normally kept in the takeoff and climb position, except when the engines are cruise leaned. There are 5 switches associated with the starting system on the aircraft. They are grouped together on the overhead panel in the cockpit. They are the engine selector switch, the starter switch, the starter safety switch, the ignition boost switch, and the primer switch. To operate the starter for an engine, that engine must be selected and both the starter and safety switches must be depressed. These are control switches which energize a power relay in the firewall junction box. An induction vibrator or boost is provided which supplies voltage for starting at engine RPM too low for adequate magneto output. The induction vibrator is located behind the overhead switch panel and can be heard buzzing when it is operating. Voltage from the induction vibrator goes to the engine selected on the selector switch. The induction vibrator energizes only 9 plugs, so only half the cylinders are firing at low RPM while starting. It is not necessary to depress the safety switch for induction vibrator or prime operation. When the primer switch is depressed, the primer solenoid for the engine selected opens and permits fuel to flow from the supply chamber of the carburetor to 2 jets in the blower throat. Either the boost pump or the engine-driven fuel pump will supply pressure to the primer. Fuel flow from the primer should be sufficient to operate the engine smoothly at 800 RPM with the mixture control in idle cutoff. It is possible to energize all 4 primers simultaneously by use of the all-engine prime switch located on the overhead switch panel. This switch could be used to obtain smoother engine operation if all 4 carburetors were iced. A blue indicator light illuminates when this switch is on. The light will also illuminate when the number 1 engine is being primed with the primer switch. The R2800 engine produces a wide range of heat from combustion. The engine has temperature limits it must operate within. Therefore, there must be a means of controlling heat dissipation. To provide cylinder head temperature control, the engine has 8 cowl flap segments, 4 to a side. They are powered by a reversible DC motor mounted on the oil cooler. Through a rigid drive shaft, gearbox, flexible drive shaft, and jack screws mounted on the segments, the flaps are opened or closed. The DC motor is protected by limit switches in the full open or closed positions. The motor has a magnetic brake to prevent coasting and permitting accurate cowl flap settings. Each set of cowl flaps is positioned by either of 2 controls. One is a 4-position selector switch on the aft overhead panel. The 4 switch positions are off, open, close, and positioning. The switches operate like the switches on the oil cooler doors in the off, open, and close positions. When the cowl flap switches are in the positioning position, control of cowl flap settings is accomplished by the cowl flap positioning rheostats, which also serve as cowl flap position indicators on the upper instrument panel. Positioning the rheostat starts the reversible motor in the proper direction. A follow-up system stops the motor when the cowl flaps reach the desired setting. Limit switches protect the motor in the full open and closed positions. There are 3 sets of engine instruments that indicate engine power output. These are the engine instruments used to set various power settings required for flight. To record engine RPM, there is a tachometer generator mounted on the rear section of each engine. The generator produces three-phase AC current, the frequency of which varies directly with engine RPM. The same generator is also used for prop synchronization. The current is conducted to the receiver, which duplicates the speed of the generator. The resultant is displayed on a dual tachometer indicator on the engine instrument panel. Because this system is self-generating, there is no circuit protection. A manifold pressure probe samples the pressure downstream of the engine blower and transmits it to a sealed bellows mounted on the manifold pressure gauge. Through a lever and gearing, the indicator hand indicates the pressure in inches of mercury. The most accurate method of measuring engine output is to measure the torque, or power delivered to the propeller shaft. This is accomplished by taking engine oil pressure, boosting it to a pressure suitable for use, and applying it to one side of a movable gear in the prop reduction gearing. A series of torque meter cylinders measure back pressure developed by torque. This pressure is sensed by a Magnuson transmitter located on the 1 o'clock position of the engine and recorded on a gauge on the engine instrument panel in pounds per square inch. This has been a general description of the engine and its systems. Your instructor will now discuss operation, troubleshooting, and emergencies.